Today's topic is just a little bit more of the introduction for what we're doing here. So the next 6 lectures, we have 6 guest lectures, 6 members of the computer science faculty will be here to talk to you about specific kinds of artificial intelligent machines. We've divided them up into 6 categories of increasing learning power. This is what I want to discuss today. One of the motivations for this is something that happened to me when I was a graduate student myself in computer science. I learned of a MIT professor named Noam Chomsky. Some of you have heard this name before. He's a famous linguist. He's still very active after all these years. But Noam Chomsky had, the time I was there, he had postulated that we could characterize computing machines into a series of levels according to their computing power. And he had 4 levels, but there's only 3 of them are really important. For those of you who might have heard this before or know a little bit about computer science, there's a category of computing machine called a finite state machine. And it's basically a model for a logic circuit in a computer. So any logic circuit could be modeled by that level of machine. And he also defined a next higher up level, which was called a push-down machine. And this type of machine came to be used for building compilers to translate source code into machine code when you write programs. The highest level in his hierarchy was a Turing machine. This is the general machine proposed by Alan Turing in 1936 to model any type of computation that anybody could possibly conceive of. So that was Chomsky's idea, was that there were levels of machines of successively more power culminating in the Turing machine. Now we're not going to go into any of this today, but I'm pointing this out to you because there was a technical thing going on a long time ago about levels of machines of increasing power. And we had a question in the modern day of whether we could sort out artificial intelligent machines of the kind that we encounter in practice all the time into a series of levels. And that's what I want to present to you, is we found a series of levels. We, in this case, being my colleague Ted Lewis, who's a former chair of computer science department, is now retired. But Ted and I have been thinking about this question, and we decided that it is possible to organize the existing AI machines into a series of levels of increasing power if power is measured by learning ability. So learning simply means that the machine acquires a new capacity to do something new that it couldn't do before. It acquires an increase of function of some kind. And so what we've got here, we're going to discuss in the next few lectures is how we could organize the existing AI machines into a series of categories according to increased learning power. So that's what I want to introduce to you today, and then you'll get the guest lectures going into depth on these issues. So let's begin with today. So that's our topic for today, a hierarchy of AI machines. The objective in this talk is to classify existing AI machines according to their learning power. So we want to be able to compare their abilities, limitations, and risks by saying this machine is more powerful than that one, and what new ability does that bring that we like, and what kind of risks does it bring with it that we have to watch out for. We'll give plenty of examples as we go through. I won't be giving a lot of examples today, but the guest lecturers will be doing that. And one of the outcomes we'd like to achieve here is we wind up with a precise common language for discussing AI machines. When we use the term learning, we simply mean that the machine or a human being, if the human being is learning, or an animal, if it's an animal learning, acquires a new capacity for action, a new function that it didn't have before. And so we're trying to be a little bit formal about it. We could say one machine like A is more powerful than another machine B if A can perform functions that B cannot. And sometimes it helps to have a little diagram. So here's a little diagram of two machines represented as black boxes. A is a more powerful machine because it includes B, and B is less powerful. It can do some of the things A can do, but not everything. So that's all we mean by learning power. So learning means the machine is going to learn to do something new that it didn't know how to do before. Here are the basic categories that we came up with according to learning power. So there's 5 we're going to be talking, 0 through 5, that's 6 total. We'll be talking about in this course. So the basic automation is the baseline, where we started from. This is historically, automation is a very old topic. People have been worried about machine automation for centuries. So we'll look into that a little bit and learn some lessons from the history of that. Rule-based systems at level 1 is basically anything you can program using standard programming. In the case of artificial intelligence, it included logic programming because a lot of intelligent actions were attributed to people because they're able to be logical. Supervised learning, the second level, is a machine that gets trained by showing it examples. So it starts out with no function, and then you show it lots of examples, and it learns the function. For example, you want it to be able to recognize faces, so you show many examples of photographs and label them with the names of the people whose faces are in the photographs, and if you show it enough of these things, after a while it'll be able to do it on its own. So that's supervised learning because there's somebody there training it. Unsupervised learning means the machine learns to do something, but there's no outside person or agent teaching it. It's learning on its own. Human-machine teaming refers to the combination where the human and the machine work together to accomplish some task that neither one could do alone. So this is actually something we do all the time. Anytime you use a computer, you're getting functions from the computer that you can't do on your own. And you and the computer are teaming up, for example, to do your homework or to write up a report, to communicate with somebody else, to do a PowerPoint presentation. So all those things are elementary forms of human-machine teaming. So this is not an idea that's unique to AI, but AI has added its own flavor to this. And finally, level 5 in this discussion will be what we call the aspirational machines. These are machines that the AI researchers and others dream about, but so far nobody's built, and nobody even actually knows whether they could be built. They hope they could be built, but nobody's sure they can be built. So there's a lot of aspirations going on around this. So those of you who were asking the other day about the singularity, that is a part of that aspirational conversation, because it's talking about a possible future in which the machines become super intelligent and then maybe do things we don't like. Maybe they don't like us, or actually it would be they don't like our descendants because it might take a while to get to a super intelligent machine. Anyway, so that's the basic hierarchy we want to talk about, and then as we go through the coming lectures, you'll see many examples of these types of machines. So one of the questions that comes up is, I said this, we're going to classify existing AI machines according to their learning power, but since the word is artificial intelligence is attached to these machines, why don't we classify them by intelligence power, okay? And we said last time, this is a very difficult task because nobody can really agree on what you might call a scientifically solid definition of intelligence. So intelligence is ill-defined. There are disagreements among the experts about what constitutes intelligence. Some people say only humans can be intelligent, but others will say, no, my dog or my cat has some intelligence. And so there's degrees of intelligence in different creatures. So which, even if we could completely identify all the degrees of intelligence, how do we characterize the type of intelligence that humans have that dogs don't have, for example? So there's a lot of disagreements around issues like that. And then, as we mentioned before, there's the moving goalpost problem, which is that every time somebody thinks they've come up with an intelligent machine, most people will look at it and say, well, it's only a machine. I don't see any intelligence hiding out in the wiring of this machine, so I'm not convinced that particular machine is intelligent. So that's another problem when we try and use intelligence as a way to try and characterize machines. There is a near universal agreement that the existing machines are not intelligent. Even though they carry the name artificial intelligence, it's, scientifically it's not intelligent. Along with all of this, there's a couple of terms that I want to say a little bit more about today. You'll hear some of the speakers speak about these things again. We mentioned one of them last time, the Turing test. Alan Turing, a pioneer in computer science, articulated in 1950 a way to try and approach the question of whether a machine is intelligent. Because he himself said, hey guys, we can't seem to agree on what is intelligence, so I'm not even going to bother to try and define it, but I will show you that there's a possible thing he called an imitation game. So the computer is going to try and imitate human intelligence, and I, as an interrogator, get to ask the computer and a human being questions, and I have to figure out which one is which. So that's the Turing test. Well, this is still discussed today. A lot of people still talk about the Turing test. And unfortunately, it's also very controversial as to whether it actually says anything at all about intelligence. And the word ELIZA up there, I want to talk about that for a moment. Here it comes up. ELIZA was a program written in 1966 by an AI pioneer named Joseph Weizenbaum at MIT. And Weizenbaum was troubled by the claims that people were making about the Turing test. And he said, I will show them, I'll show my colleagues, an example of a program that many of them will believe is intelligent. But once they learn how it works, none of them will believe that it's intelligent. And he called this program ELIZA. And ELIZA, as you'll see in a moment, was a program that simulated a conversation with a Rogerian psychotherapist. So, he picked Carl Rogers as a prototype or an exemplar of psychotherapy that he wanted to imitate, and had a machine that seemed to carry on a conversation that sounded like if you'd gone to a session with Carl Rogers, this is what it would sound like, what it would be like. And some people, in spite of being told that it was only a machine, continued to believe that it was intelligent. Weizenbaum was telling a story about his own secretary, who would sneak off when nobody was around during lunchtime. She'd log in through her computer terminal and talk with Eliza and deal with her whatever issues she wanted to with Eliza. And one day, Weizenbaum finally told her, he said, hey, this is just a program, it's a machine. There's no psychotherapist out there talking to you. There's nobody knows anything about psychotherapy. Even I, the author of the program, don't know anything about psychotherapy. So it's not real. And she said, it is. It's helping me solve my problems. And she refused to believe that it was a machine. So he said, this is his example of how people can be willing to believe that a machine is intelligent even when you can show them that it's not. So here's a screenshot. Turns out if you do a little Google search, you can find ELIZA programs online, and you can talk with them. You can see what it's like to have a simulated conversation with a psychotherapist. So here's the sample. I'm not going to read it to you, but you can take a look for yourself, and you can see this kind of thing here. The ELIZA program is asking you questions, and you'd say something, and then it would ask you a question about what you just said, and then you'd say something to that and ask you another question about what you just said, and it keeps going back and forth. And so I just stopped after one screenful and present that to you here, so you can kind of see what the kind of conversation is. And those of you who might have come in contact with Carl Rogers' type of psychotherapy might see this sounds a little bit familiar. And this is the sort of thing that the Weizenbaum's secretary was doing at lunchtime and believing that she was talking with a licensed therapist. Well, here's another session that I had, because when I'm a human interrogator talking to a machine that's supposed to do something, I want to find out which is which. And so one of the favorite ways of attacking a machine is to keep asking the same question over and over again without changing it, and see if you get the machine to go into a loop and start repeating itself. And that's what happens here. So the machine would say, please say something, and I'd just say, what's been bothering me? And I kept saying that over and over again, and the machine kept trying to ask about that, and eventually it started to repeat itself. So if you were looking at this, after looking at a screenshot like this, you'd say, that doesn't sound like a real conversation with a human being. It sounds like maybe it could be a conversation with a machine that doesn't know that it already said that, and it just keeps repeating itself. So this is part of the reason that the ELIZA program had such an influence. It showed people it's possible to believe that a machine is intelligent, even though we give you conclusive proof by looking inside that it's not intelligent. The program that does this is about 200 lines of code. It's a very short program, and all it does is it scans what you type for keywords, and when it finds a keyword that matches a list of keywords, it prints out a stock answer. And it's able to, get some variety there, but 200-line program doesn't go very far, but this is what you get from it. So those of you who have programmed, 200 lines program isn't a very big program. So ELIZA is not a very big program, and so simple and small. Once you see it, you say that's not intelligent. It's not even a good parlor trick. So this generated a lot of controversy in the AI research field, that people were arguing about whether or not Turing tests, as exemplified, say, by ELIZA, is a good way to reach a conclusion about whether a machine is intelligent. And it's stuck with people, this idea that you could talk with a machine. ELIZA is stuck, and we have websites that let you talk to it yourself. So you don't have to say, I heard about this historical thing. You can actually go talk to ELIZA yourself. And if you want to have a few minutes of fun, go do it a little later, type in ELIZA to Google, and it will take you to one of these sites, and you could talk with ELIZA yourself. Okay, so going back to our original question is, if we want to assess whether something is intelligent, the best we can do, according to our current knowledge, is with things that we correlate with intelligence. So we call them, for example, learning is correlated with intelligence. So if we learn a new function, we adapt to our environment, we say that's intelligent to do that. Problem solving is another characteristic of intelligence. If we can be told a problem and then solve the problem, that takes some kind of intelligent activity. Conversation, another form. So if we can actually have what you might call an intelligent conversation with somebody, we'd say that whoever I'm talking to is intelligent. Most people would not, after they play around with ELIZA, would not say that was an intelligent conversation. So ELIZA might, if you're saying, trying to see if that conversation test actually works for ELIZA, many people will conclude, no, it doesn't convince me that I'm talking to an intelligence. Another aspect of intelligence is thinking. Of course, we get into long arguments with people about what exactly is meant by thinking, but if we look, it appears to us that a machine is thinking, we're more likely to ascribe intelligence to it. So what we have here is a number of characteristics that we associate with intelligence, and the more of those characteristics that a machine or even a person would exhibit, the more likely people are to say that's intelligent. So that's about the best we're going to do in our current state of knowledge, is look for these correlates of intelligence and see how many of them are satisfied by whatever we're talking to. On this list, learning is the most easily quantified. It's easy to tell whether something's got more function than something else. So that's why we use that to define our hierarchy of AI machines. It's clearly not the only way you could define a hierarchy, but this is the way we chose to do it. Okay, now I'll just point out that this problem of trying to figure out what is intelligence and build machines is similar to the problem that biologists have. Biologists are interested in the question of what is life? And a substantial part of biology is actually devoted to trying to answer that question. The biologists haven't been able to agree on a unique definition of how you tell that an organism is alive. What they have done is they've come up with 7 criteria, and here they are. These make more sense to biologists, but they're nutrition, respiration, movement, excretion, growth, reproduction, and sensitivity. So each one of those can be assessed, and if you have an organism that you're looking at that satisfies all 7 of those, almost all biologists will say it's alive. If you have an organism that you're looking at that only satisfies 1 or 2, you'll have big arguments among biologists about whether it's alive. There's been recent news reports about new kinds of strange bacteria found deep in the ocean around hot lava flows, and the biologists argue about whether they're really alive or not, because they don't satisfy the whole list here. So biologists have the same problem. But you notice that it's possible to have like a holy grail, like what is life, and you can't answer it, but we can tell when we're going to argue about it or not, but that doesn't stop us from doing good biology. And the same thing with intelligence. We could argue about intelligence, but that doesn't stop us from building machines that do useful functions and learn how to do them, which is what we're going to be talking about. So we use these kind of criteria to assess whether life is present. We could use the intelligent correlates to assess whether intelligence is present. But whether or not we do that doesn't prevent us from building machines. Another problem that comes up is even the same kind of problem is the consciousness problem. You notice on the list of correlates of intelligence, I could have put consciousness there, but people want to argue about whether consciousness is a correlate of intelligence, because they will argue that my dog is conscious, but not intelligent at the same level as me. So it's hard to make a one-to-one connection between being conscious and having intelligence. So neuroscientists and brain scientists are interested in this question because when is a person conscious? So if you go into a hospital and you have somebody who's on life support, they have these big arguments about whether that person is conscious or not. If the person is conscious, they do the life support one way, and if not, they get into arguments about whether to take them off life support. So this is a very real problem for doctors and physicians. When is a person conscious? And then a more researchy problem is what kind of consciousness do animals have as distinct from what humans have? Well, in the world of neuroscience, they use the term neurological correlates of consciousness. Fancy term, and they have a little acronym for it, NCC. And what it really simply means is measurable things that you could do things in a brain, like stick a probe in or put a EKG or ECG sensor on somebody's skull and measure something, and then from the measurement be able to say that the person is conscious or not. Nobody's got an answer to that. It's like a holy grail for neuroscience, is to come up with the correlates of consciousness. Well, one of the things that's emerged from this is a claim that many of the neuroscientists now say consciousness is widespread but can't be computed. That's, of course, one of these controversial things too. So computer science, AI people say, well, we're not so sure about that. We're going to continue to see if we can produce consciousness in machines. And the neuroscientists are saying, like, it's widespread, but it doesn't look to us like a machine could be conscious based on everything we can see and the way the brain works. So there's another example of one of these holy grail problems that people will follow, but we can in spite of the fact there's no answer to that problem, we can still build useful AI machines. So here again is our hierarchy. I just want to quickly tell you a little bit about each level, and then we'll do questions. So level 0 is basic automation here. So here, this is dealing with a baseline of things that most people wouldn't consider intelligent, at least up until the current age. So we've talked about automation of jobs and factory processes and all sorts of things for centuries. And this automation has been a source of a lot of uncertainty, social unrest, and other things. So this is an old problem, is when we automate stuff, what are we trying to do? Well, we're trying to build a machine that will do a process that human beings used to do, but maybe do it better and be more reliable about it. So in this talk, which will be given by Josh Kroll of the computer science department, he's going to look into a whole bunch of examples of traditional automation. There's some surprising examples out there. And he's going to pull out of them a few features that apply to all automation. His examples will point out we've had automations long before there was artificial intelligence. We've had automation long before there was computing. And what happens in the computer age is we added software to the automation so we could automate processes by writing software. And then the artificial intelligence age, we go further, and some of the software could be artificial intelligence software. So we can have automation supported by artificial intelligence software. One of the things that Josh will show you is that there's a very large question associated with automation, whether it's classical automation or current software automation or artificial intelligence automation, is the question of whether the machine that's doing the automating is reliable and trustworthy. Because some of these machines get extremely complex, and it's really hard to tell whether they work as intended. So this is a source of a lot of controversy among many people who are users of artificial intelligence, and Josh will show you where it comes from. In level 1, the rule-based systems, here the idea that we're looking at programmed systems that make logical deductions from an input with the help of a database of facts and rules. So we record everything we think is a fact that pertains to the situation into the database. Everything we think is a rule pertaining to the situation, we put that in the database. And then we have a programmed system that's taking a particular problem as an input, doing a lot of database lookups, trying to apply all the rules and facts and tell you a good answer to the problem. So early examples of this type of thing were chess and checkers. So in 1952, for example, there was a chess program written by a man named Arthur Samuels at IBM. It played pretty good chess. And so it was the first example of a machine playing a game that most people thought was a human intellectual game. So Samuel's chess program, the checkers program, inspired other people to say, well, let's do something more significant. Let's see if we can find a machine that plays chess. So that's how we got into the business of artificial intelligence machines that play games. A category of systems that got examined at that time, starting in 1970s, was called expert systems. These were supposed to be software systems that would solve problems with the same degree of agility and smartness as an expert would solve the problem. And the idea was we're going to go interview the experts, capture all their knowledge, the facts that they know, all the rules that they apply, put it all into the database, and then the expert system is going to, when you show it a problem, it's going to come back to you and say, here's my answer, and the answer will be as good as the actual expert. So that was the dream. This never worked out. So Vinny Monaco will be talking about that, talking about why this was never quite worked out and what have expert systems actually accomplished, but why they're not real experts. They become competent at some things, but they're not experts. Well, level 2 is supervised learning. This is probably the one you've heard the most about, because you've heard about machine learning, where you show a machine lots of examples of something and it learns how to do something useful. So a very common example is machines that you show them a photograph and it will tell you the name of a face in the photograph. Now this has become so common, you have it on your phones. You can have, or Facebook will do the same thing. Facebook will examine photographs that you put up there and it will actually tag them with, oh, that's my friend George, or that's my friend Alice. So this is what has been accomplished at this level. We've got programs that will do that. We teach them how to recognize faces by showing them lots of pictures of people's faces along with the names of the people in the picture. And after enough, show them 1 million pictures or 10 million pictures, the machine will be able to do a pretty good job of saying who's in the picture. And they're able to do it and put it on a phone, so you can do that yourself, or you can put it in Facebook, and Facebook will do it for you. So that's kind of what we're doing here. It's the most common example with supervised learning. It's called supervised because the process of training the machine is supervised. Somebody's saying, here's a photograph, here's the name of the person in the photograph, and then they adjust the machine so that it gets it right. And they keep doing that over and over and over again. So it's all supervised. The machine is doing what the human being wants it to do. And then finally, when all the photographs have been shown, the machine is let loose to recognize pictures. Well, these things turn out to have some peculiarities to them that are now subjects of research. For one of them is we're never quite sure what happens with these trained machines if you show them an input that is never seen before. So the inputs you've shown them, we call that the training set. But the hope is that you show it photographs that haven't been shown and it still correctly identifies people in those photographs. So unfortunately, we don't have enough trust that these things work, that if you show it a new photograph or give it a new input, that you're confident that the machine is going to do the right thing with that new input. And there's been enough tests with these things where they say, oh, here's a machine doing something stupid when I gave it a new input, so we got to do some more work here. That obviously has implications if you want to put something to use in the field or a military application. You don't want to put an artificial intelligence system into play unless you're confident it's going to do the right thing when presented with new inputs it hasn't been trained on. Another thing that happens with these things is it turns out that you can take trained inputs and mess them up a little bit. Change a pixel here and a pixel there, and if you strategically do it right, the machine will get completely confused. And Marco Oriskinen will be talking to you about this next week and he'll give you specific examples of this where people have taken trained machines and taken some of the valid inputs and messed them up a little bit, and the machine gives a completely wrong answer. This has spawned a whole area of research now called adversarial machine learning, where they're trying to figure out how do you attack somebody's artificial intelligence by, say, presenting it with slightly off inputs and see if it will drive the machine crazy. Well, the next level up is the unsupervised learning. This is where we take away the external trainer that's showing the machine what's the right thing to do. One of the problems with that is that you need these enormous data sets to train things. So you want to have a vision recognizer, you need tens of millions, hundreds of millions of photographs, all completely labeled according to who's in them, to show the machine so it can learn how to recognize the faces. Well, somebody got to do the work initially to say, here's, you get this huge stack of photographs, and they got to have somebody label them. And how that's done today is with human labor. Somebody's got to sit there and look through the photographs and say, oh, that's Jane, that's Jack, blah, 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 and wind up with a set of labeled photographs. That's extremely expensive. If you want 100 million labeled photographs, that's extremely expensive. So unsupervised learning is saying, can we have machines that don't need to be shown lots of examples, but figure it out for themselves? And that's called unsupervised learning. And one example of this was machines that can classify unknown data into classes. So I know of an early experiment at NASA that took place. A researcher, an AI researcher, had a database of NASA, what was it, sky infrared telescope readings, which something like 5,000 stars, or they call them objects, had been recorded, and along with each one was a little bit of a spectrum of their light. And the machine classified the stars into groups that are similar to each other. The machine came up with something like 275 groups of stars out of the 5,000, grouped them all together. And when the results were shown to the astronomers said, this is amazing because they got all the classes right. So this was kind of a test, a feasibility test. So the machine classified the objects without having any guidance from an astronomer into the same classes that the astronomers themselves had found previously. So I always thought that was pretty amazing that the machine could do that, but the people who did that were very pleased with that. One of a cute little twist in the story is there was one place in the machine classification that differed from the astronomers. The machine found a new class of stars the astronomers had not seen. And when they looked at it, it said, machine has made a discovery. We didn't see that before, now we see it. So this definitely some kind of power there if you know what you're doing, that you can get a machine to do something like that. Take the data and organize it into all the objects that are similar to one another, put them all together into a group. Another place where this has been very powerful is with board games such as chess and Go. You've undoubtedly heard the stories recently about the Go grandmaster who was beaten by a machine. Nobody had been able to build any kind of machine that could approach Go. It's such a difficult problem. It took 30 years to build a chess machine that would beat a grandmaster chess. But the subsidiary of Google called DeepMind created a machine called AlphaZero that figured out how to play grandmaster level Go in 13 days. That is a very significant breakthrough, in my opinion. So Dr. Chris Darkin will be here to tell you about these kind of things. And so you'll get a little more insight into what's going on with unsupervised learning. Human-machine teams are simply designing things that you want, jobs that you want done that have some components of doing the job are done by machines and others are done by humans. So we do this all the time, collaborative groups in the internet, lots of things where we have humans and machines doing things together. Machines are given the tasks that machines are good at, humans take on the tasks that humans are good at, and we have a nice, well-designed interface that lets them all work together smoothly. So this is a very rich area of investigation in artificial intelligence, and it's of great interest in the military because at least in our military, we're always concerned about having a human in the loop. So we want to be able to take advantage of machine-like things, but we want human judgment to be reserved for the commanders who have to make the actual decisions to use the machines. So Dr. Rudy Darkin will talk about this issue, the human-machine teaming, and the way we go about trying to design interfaces so that humans and machines can do this successfully. And level 5 is the aspirational level. So this is all the other stuff that you hear about artificial intelligence that people dream about but haven't yet figured out how to do. And maybe they never will, nobody knows, but there's lots of debate here. So, an example of the debate is your brain, is that a machine? If it is a machine, then we should be able to build a neural network that looks exactly like a brain, and it would be intelligent. The neuroscientists don't agree with that conclusion. So there's a lot of debate over that issue, and there'll probably be a lot more debate as people continue to explore it. Another issue is the one that is exemplified by the singularity. So the singularity is this idea that we keep building more and more powerful machines, and maybe by 2030 or 2050, we'll have the ability to build a machine the size of a human brain with the same number of transistors or components inside of it as the human brain, and the same number of connections between them as the human brain, and anything like that would develop its own intelligence. And then the speculators go on and say, well, if it develops its own intelligence, it might decide that it doesn't like human beings because they're weak and they're not as smart. They can't do things as fast and reliable, and the machines look for ways to eliminate human beings. So that Hollywood loves that story. So Neil Rowe will discuss all these kind of issues about what is aspirational, what is likely to be done in the future, what's probably not likely to be done, and he'll expose some of these controversies that exist around those questions. And as I pointed out before, the answer to those questions, there may never be a good answer to some of those questions, but that does not stop us from building useful AI machines today. So that's basically what we're going to be doing in the next few days. And that's the end of my story for today. Last time we left you with a couple of addresses up there for websites. The webmaster moved some stuff around. The first one up there, first address is correct. It's the address for the consortium, and from that page you can find a link that will take you to the lecture list that we're working with here. The second thing up there is attempting to go directly to the lecture list, but they moved the link, so the second one doesn't work. So if you're trying to go to the web page and see exactly what the lecturers have said so far and get copies of the slides of the lecturers, and eventually get a copy of get a link to the video of today's talk or any of the talks, all of that will be on that page. So you can get to it by the first URL up there.